Hello guys, welcome to today's lecture. We are gonna start chapter 6, which is concept of continuum. So chapter 6 is all about concept of continuum and what is thermostatics. So let's begin. What exactly is continuum? So to understand what is continuum and why was it created in the first place? I mean, don't we have enough thing to complicate thermodynamics? Now, why is this continuum over there? So we try to understand why concept of continuum is what it is, why is it essential in thermodynamics. So over here, I have a picture of a single molecule and then a collection of molecules. So on the left hand side, while you can see a picture of molecule, and on the right hand side, you can see a collection of different molecules. So this single molecule and this is a collection of molecules. Now, when I talk about continuum, continuum is simply we are talking about many different molecules and we are taking that space which has many different molecules, particles, atoms, whatever you want to say, and they are behaving in the same way. Okay, so this is a collection of particles, molecules, atoms, whatever you want to say, which are behaving in the same way. This is a single molecule on the left hand side. This is a single molecule. Now, why we define concept of continuum? Because if we do, why was thermodynamics designed? To improve the efficiency of steam engine, then heat transfer came, all that thing, to improve system, to improve a system, right? To improve the efficiency. That's the goal of engineering. To improve the engineering, to develop science. So that's the reason. So if thermodynamics was designed for that, now there are several concepts which are designed around thermodynamics. One of them is continuum. Continuum plays an essential role in assigning a thermodynamic property to a system. So if you're talking about a thermodynamic system, we need to assign a thermodynamic property to it, temperature, pressure, volume, so that we can do calculations. We can prepare charts, plots. Otherwise, if everything is random and spread, there would be no thermodynamics. How would you calculate things? So to assign a property, a thermodynamic property, it is very difficult to do so for a single molecule. The reason being this single molecule is like the mischievous child who is making random moves, who is in and out of the system, who is changing its position with time. It's not constant. It's very difficult to assign this any property to a single molecule. But we can assign a property to a collection of different molecules or particles which are behaving in the same way. And we can assign a thermodynamics property to it. We can assign a temperature, pressure, volume. That's the reason we study continuum. Now, when it comes to mathematics, everything has to be defined in mathematical relation so that we can make calculations. So guys, let's take concept of continuum and understand it through a thermodynamic property. So first we have density here. So in front of you, I have a green circle. In its center of the green circle, I have a point P. It is surrounded by a mass delta M and volume delta V. So this yellow space has a volume delta V and mass delta M. Delta M and delta V both are very small volume and mass, infinitesimal small volume, infinitesimal mass. Now, if I define density, density is defined as mass per unit volume. So I can simply say my density is delta M by delta V. Or can I say this? Is this true? We don't know yet. The reason is I don't know if this delta M and delta V, especially delta V, is large enough so that I can apply the concept of continuum on it or not. So to understand it, let's see if we have a space and I want to assign any thermodynamic property to it, that space should be in thermodynamic equilibrium with the surrounding. So that system should be in thermodynamic equilibrium with the surrounding, and also that system should have significant number of molecules so that its property, whatever property we assign to it, doesn't change with time. Then only the concept of continuum is valid. So if we have a very small system, let's say I have this delta V, and delta V is such that there are two molecules in it. So if I take the density now, the density will be weight of mass of these two molecules, which could be, let's say, delta M1 plus delta M2 divided by the volume, delta V. So this will be the density. Now, since there are only two molecules, and these molecules may leave the system with time, they are not at one single point, they may leave the system. So if one molecule leaves the system, now what my density becomes? My density now becomes delta M1 by delta V. So this was at time t1, this was at time t2. So you can see my density got affected by a large amount. But shouldn't my density remain same for a system? Otherwise, how can I define a property to a system if it is not remaining same with time? I cannot even define velocity at this point because the average or instantaneous velocity will change with time. That's the reason we need a collection of different molecules. So let's say in the same volume we have large enough volume that we have 10,000 molecules. So now this will become delta plus 3 up to 10,000. And even if one single molecule out of these 10,000 molecules leave, my density is not going to change significantly, right? At least it is better than having two molecules. So now I can clearly say that this 10,000 points is the minimum limit from above which I can define a thermodynamic property, or I can assign a thermodynamic property to this system. From here, the continuum starts, and we can understand it through a graph. Let's just erase this thing from here and try to understand it through a graph. So I have a plot of density versus volume. Now, as I increase my volume, my density is going to decrease. It reaches at a point after which it is constant. This is the density. Now, this point, this is delta V dash. At this point, I have enough molecules or particles which are behaving in a similar fashion so that I can assign a thermodynamic property to it. Now, before this, I'm saying my thermodynamic density was decreasing, but it's not true. It can take any path. We don't know. Could be like this, could be like this. It could be any path before this. So we clearly don't know what's the density of the system before this point. Let's call this point A, a continuum point. So we don't know what's the density of a system before this point A. It could take any path because even if one molecule leave, it's gonna affect the density or a property of the system. That's the reason why concept of continuum is applied. Now, where is this concept of continuum not valid? So this concept of continuum is not valid where there are very few molecules like high vacuum systems, electron tubes, rocket propulsion, and there are many other applications where concept of continuum is not valid. Each molecule behave in its own fashion. Each molecule, particle, electron, atom, whatever it is, it behaves in its own fashion and you have to study that. And the concept of molecules as a whole or a continuum fails there. It's not valid. Okay, now comes a very interesting part where thermostatics and thermodynamics is. So should we call it thermostatics, thermodynamics? Why having this conversation? Therm means heat, statics is it is in a place, it is not changing its position with time, and dynamics is motion. So whenever we do thermodynamic calculation, we always say that the system is in thermal equilibrium with its surrounding, right? It means that there is no mechanical non-equilibrium, there is no chemical non-equilibrium, there is no thermal non-equilibrium. That means it is in thermal equilibrium with the surrounding. So it's not changing its state. The system is not changing its state. But in thermodynamics, there is motion. The system is changing its state with the surrounding. So how can we assign any property to it? Because it is changing its state, how can we assign a property? So shouldn't we call it thermostatics rather than thermodynamics? Actually, that's true. Thermodynamics, it's kind of a misnomer. But in real application, in real world, a system always attain a state of thermal equilibrium only after it goes through a process of non-equilibrium. In real world, everything is not stationary, right? It has gone through a system of non-equilibrium processes to achieve thermal equilibrium, and that's why we use thermodynamics. So using thermodynamics is not wrong. Still, many people argue on it. We should call it thermostatics, thermodynamics. But since we are talking about real applications, real world, we cannot say it is thermostatics because that will imply that thermostatics means everything is in thermal equilibrium, which it is not. To achieve a state of thermal equilibrium, it goes through a path of non-equilibrium. That's the reason we call it thermodynamics. So I will finish this lecture here, guys. If you like the video, please like it and share it among your friends and who may benefit from this lecture series. Also, please subscribe to the channel. This encourages me to put on more videos like this. And I'll see you on the next video. Thank you guys. Have fun.